right, now we're going to go through this investigation using a different base. So I'm going to use the second most common base, and that is the base 2 system or the binary system. This is the number system that actually makes all of our computer technology function. So just like we did with base 10, we're going to think about the base 2 number system. So the digits in the base 2 system would start at 0, because again, you need a way to represent nothing. And you only have 2 digits. So as soon as I list the digit 1, I stop. If this was base 5, my digits would go 0, 1, 2, 3, and 4. Like we did with base 10, I'm now going to write out the exponential expressions that will form the position values in this system. My base is 2, so I put 2's all the way across. I always start my exponents at 0 because remember, anything to the 0 power is 1 and gets me the 1's place. Unlike the base 10 system, we're not going to have tens and hundreds and thousands. 2 to the first is equal to 2. So in the binary system, you have a 2's place. 2 squared is 4. So the next position is the 4's place. 2 cubed, 2 times 2 times 2 is 8. So we also have 8s and we have 16s. And that may sound very strange, but keep in mind, the only reason that you're used to a 1's place and a 10's place and a 100's place is just that that's what you've experienced for many, many years. There's no reason it can't be a different base and have positions of 1's and 2's and 4's and 8's. The first thing you're going to be asked to do in this investigation is to represent different numbers in your number system. You're going to be able to choose any base that you want to work in other than base 10 or base 2. Please remember that the subscript here just indicates that I'm talking about the number 7 in base 10, which is the 7 you all know and love. We're going to write this number as a binary number, a base 2 number, and then we're going to write it as powers of our base. And our base, again, will be 2. So I'm going to set up the same kind of chart that we've been working with. I've set up a basic table, and I'm now going to fill it in with my base 2 positions. And here's how I figure out what a 7 should look like in this system. You take the number, and you look for the first position that is less than your number. So if my number is 7, 16 is bigger than 7, so I will not begin here. 8 is bigger than 7, so I will not begin here. The first position that's smaller than my number is 4. So what I'm going to ask myself is how many 4's fit inside 7? Or said another way, I'm going to subtract a 4 and see how much is left. I get 3. Can I subtract another 4? No, because that would take us into the negative numbers, which is not a place we're going to go. Therefore, my digit for the 4's place should be a 1 because that indicates this number is made up of 1, 4. Now I move to the next position, 2's. How many 2's can I subtract? Well, I subtract 1, 2, and I'm down to 1. And because 2 is bigger than 1, I can't subtract another. So I can subtract 1, 2. And how many 1's fit in what I have left? Well, just 1. 1 take away 1 is 0. So the process is complete. And I used 1, 1 to make this 7. The base 2 representation of 7 is the number 1, 1, 1. And I mark it with the little 2 so that you know I don't mean 111. I mean 111 in base 2, which is 1, 4, 1, 2, 1, 1. To represent this as powers of my base, I do the same thing we did in base 10. The first one is the number of 4's, or as a power of my base, as a power of 2, that's 2 squared. I combine it with 1, my digit, times 2 to the first power, plus 1 times 2 to the 0 power. And if you actually do all the math on that, 1 times 2 squared is 1 times 4, which is 4. 1 times 2 to the first is 2. 1 times 2 to the 0 is 1. And you can see I get a 7 in base 10. So this is how you would write my answer as powers of 2. So my two answers for this particular question would be here and there. All right, now what about the number 24 in base 10? What would that look like in base 2? And remember, the only digits I'm allowed to use are zeros and ones. So it's going to be some mixture, some combination of the numbers 0 and 1. I'll start with the same table I used in the last example. I begin with the number 24. In your table, you always want to make sure you have a position that is bigger than your number. My biggest right now is 16, and I need to check and see what the next biggest would be. In which case, you just bump out your table, make this the 2 to the 5th column, and 2 to the 5th turns out to be 32. So this is the 32's place, which again sounds weird, but begin the same way where you look for the first position that is lower than your number. 32s are not, so it turns out I'm not going to need this spot, but it's important to check. 16s. Can I subtract some 16s out of 24? Yes, I can, leaving behind 8. Can I subtract another 16? If I could, I'd put a 2 in this spot, but that's not going to be possible because this is the binary system. It's either going to be 1 or 0. So I'm going to put a 1. The next position is the 8's position. Can I subtract an 8? Sure. How many times? Just once, because then I've reached 0 and I'm ready to stop. So 1/8 fits inside of 24. So what I've just shown is 24 is made up of 1/16 and 1/8. Now it is important to represent the other positions because just like when we mean 100, we don't just write down the 1. We put the 2 zeros to indicate what position it's in. I need 0 in all the other positions. Therefore, I know that the number 24 in base 10 looks like 11000 in base 2. Now I'm ready to write this as powers of 2. It would be my digit 1 times 2 to the 4th plus 1 times 2 cubed plus 0 times 2 squared plus 0 times 2 to the 1st plus 0 times 2 to the 0. And just as before, if you actually do the math on that, you'll find that it does arrive at a total of 24. The next number I'm going to write in base 2 is the number 3071. I do need to expand this table out because 32 is not close to this number at all. So I'm going to need to add some columns on until I get to the first column that is actually bigger than this number. All right, I've added powers of 2 to the left, increasing the exponent every time until I get to the first place that's actually bigger than my number, which happened at 4096. And just because of space, after I did the 64s, I switched to just writing the numbers 128's place, the 256's place, the 512's place, etc. Now I repeat the process that you saw me go through in the previous examples. The 4096 is not smaller than my number, so I ignore that one. 2048 does fit into my number, and the question is how many times? So I subtract. Can I subtract 2000 again? No. So only one of those fit. My next place is the 1024s. Can I subtract that from 1023? Nope. So that's going to be represented by a digit 0. How many 512s can I fit? Subtract it and see how much is left. Can I subtract another 512? Nope. Just one. 256 can be subtracted. What's left? Can I subtract another 256? Nope. So just one of those, and so forth. And at long last, I have finished writing the number 3071. In base 2, it would be 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1. A total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ones in a row. 6, 7, 8, 9. Oh, I missed one. 10. Aren't you grateful you don't have to like write checks in binary? And this is, of course, again, a base 2 number. All right, I don't really want to have to write this one out as powers of 2, but I will. And I'm done. And that was terrible. And just to be clear, when you switch to other bases, as you're going to have to choose a different base number, here's what's going to happen to your chart. If, for instance, you decide that you're going to work in base 5, well, in base 5, the digits are 0, 1, 2, 3, and 4. And you would create your table starting at 5 to the 0 power, then 5 to the first, and 5 to the fourth would be the first 5 positions. 5 to the 0 is 1, 5 to the first is 5, 5 squared is 25, cubed is 125, and to the fourth power is the 625th place. So in base 5, your positions, again, they're not ones, tens, hundreds. They're not like binary. They're not ones, twos, fours. Here you would have the ones place, the fives place, the 25s place, the 125s place, and the 625s place. All right, let's keep moving forward. Next in the investigation, I'm going to ask you to give an example of a 2-digit number in your base and convert it back to a base 10 number. And remember, you can only make your 2-digit number using the digits that exist in your base. So because I am in base 2, the only digits I'm allowed are 0 and 1. So for my choices of making 2-digit numbers, I don't have a lot of options. I guess I'll go with 1 followed by 0, which is not the number 10. And to make sure you know that, I put the little 2 at the end. So I'm starting with the 2-digit number 10. Now I want to convert it back to base 10. How do I do that? Well, you use the same chart that we've been using before. Now here's how I'm going to use the chart, but in reverse. My number is 10. Remember that the rightmost position is always your 1s, and in base 2, the next position over is your 2s. So fill in your number into the chart. Now I just write out that expansion that you saw me do before. I have a digit of 1 in the 2 to the first place, plus I have a 0 in a 2 to the 0 place. Okay, now you just do the math. 1 times 2 to the first is the same as 1 times 2, which is 2, plus 0 times 2 to the 0 is really 0 times 1. Anything times 0 is 0. And so in base 10, the number this represents is 2. So it looks kind of confusing. You have a 10 in base 2 is a 2 in base 10. But remember, this really is not 10. This is 1, 2 and 0 ones. And it's the same as our familiar number 2.